Assistant Professor in Andhra Pradesh State University's Electronics and Communication Engineering 2018 Question Paper Solutions Part 6, that is from question number 151 to question number 180. First question: in the output of delta modulator speech encoder, the consecutive pulses are of opposite polarity during the time interval t1 to t2 indicate that during this time interval. So if the input to the demodulator is constant, if input to demodulator is constant, then output of demodulator is consecutive pulses of opposite polarity. So correct answer is 3. The input to demodulator is essentially constant, then only the consecutive pulses of opposite polarity are obtained at the output. So this delta modulation is considered as 1 bit DPCM. So 1 bit differential pulse code modulation. The encoder used in delta modulator is 1 bit analog to digital converter. The output of the quantizer is either plus delta or minus delta. If the input to quantizer is positive, then the output of quantizer is plus delta. If input to quantizer is negative, then output of quantizer is minus delta. Therefore, if the input to demodulator is constant, if input to the demodulator is constant, then the output of demodulator is consecutive pulses of opposite polarity, either plus delta or minus delta. Correct answer is option 2. Next question. In a baseband communication link, frequencies up to 4500 Hz are used for signaling. Using a raised cosine pulse with 85% excess bandwidth and for no inter-symbol interference, the maximum possible signaling rate is symbols per. So we know that the maximum signaling rate Rs for a raised cosine pulse is given as twice the bandwidth into 1 by 1 plus alpha, where alpha is roll-off factor, and given alpha is 85%, roll-off factor is 85%, which is 0.85. This is a given value. Also, the bandwidth given is 4500 Hz. So from this signaling rate, Rs is equal to 2 times of bandwidth 4500 into 1 by 1 plus alpha 1 plus 0.85, that is 9000 by 1.85. So correct answer is 4864.86 symbols per second, that is approximately equal to 4865 symbols per second. Correct answer is option 3. Next question. Given the probability of error, at a given probability of error, the binary coherent FSK is inferior to binary coherent PSK. So these are the, for coherent PSK, the probability of error is 1 by 2 error function of square root of EB by N0. For coherent FSK, 1 by 2 error function square root of EB by 2 N0. Similarly, for non-coherent FSK, 1 by 2 exponential of minus EB by 2 N0. For non-coherent PSK or DPSK, probability of error is 1 by 2 exponential minus EB by N0. The probability of error for all modulation schemes decreases monotonically if increasing EB by N0. So if EB by N0 increases, then probability of error decreases. This is the first point. Next point is, for any value of EB by N0, coherent PSK produces small probability of error. So least probability of error is for coherent PSK and highest probability of error is for non-coherent FSK, frequency shift keying. Next point. Coherent FSK and differential phase shift keying, that is non-coherent PSK. Coherent PSK and non-coherent PSK require an EB by N0, that is 3 dB less than corresponding values for conventional coherent FSK and the non-coherent FSK respectively. The probability of error for non-coherent PSK is 3 dB less than non-coherent FSK. The probability of error for coherent PSK is 3 dB less than coherent FSK. Next, minimum shift keying has exactly same error performance of QPSK. For minimum shift keying and QPSK, the probability of error is same. Next point is, at the high value of EB by N naught, coherently detected binary PSK and QPSK have same probability of error. Coherent BPSK and QPSK have same probability of error provided that EB by N naught is very high value. Next, at high value of EB by N naught, DPSK and non-coherent FSK perform almost similar. At high values of EB by N naught, DPSK differential phase shift keying and non-coherent FSK perform almost well. So from these points, we know that coherent PSK and differential phase shift keying require EB by N naught, that is 3 dB less than the corresponding values of conventional coherent FSK and non-coherent FSK respectively. Here the correct answer is option 3. At a given probability of error, binary coherent FSK is 3 dB inferior to binary coherent PSK. Question number 154. Coherent demodulation of FSK signal can be detected by using. Coherent demodulation of FSK signal can be detected by using correlation receiver. So correct answer is option 4, correlation receiver. This coherent detection is also known as synchronous detection. Coherent detection is also known as synchronous detection. So this is a coherent binary FSK receiver is given. Coherent detection requires replica of carrier wave of same frequency and phase at the receiver. The received signal and replica of carrier are correlated using information contained in their amplitudes and phases. In case of non-coherent detection, it does not need any reference wave. It does not exploit phase reference information because envelope detectors are used in non-coherent detection. This non-coherent detection is less complex, but the performance is worst when compared to coherent detection. So this is a circuit diagram for non-coherent binary FSK, where we are using envelope detectors. No phase reference phase signal is not required. Therefore, correct answer is coherent demodulation of FSK signal is detected by using correlation receiver. Next question. If the symbol probability changes from equal to non-equal value, then entropy will be. Obviously, it gets decreased. This entropy is maximum when when all the symbols are equiprobable. If symbol probability changes, this is probability axis, probability of symbols, and this is entropy H. If symbols are non-probable, then probability of error, entropy decreases. If symbols are equiprobable, that is if all symbols are same, then entropy is maximum and the maximum value of entropy is 1. The definition of entropy is it is a measure of average information content per source symbol, and it is given as entropy is equal to sigma pi log to 1 by pi bits per symbol. Entropy contains maximum value if symbols are equiprobable. If symbol probability changes from equal value to non-equal value, entropy will gets decreased. Correct answer is option 1. Question number 156. In a digital communication system, transmission of successive bits through noisy channel are assumed to be independent events with probability p. Here the error probability is p, and the symbols are assumed and the channel is assumed to be to be in independent events. The probability of at most one error in the transmission of 8-bit sequence is given n is equal to 8. This binomial distribution can be used b of n comma p is equal to ncr p power r 1 minus p n minus r. This is binomial distribution. Here probability of error probability is p and probability of correctly received is 1 minus p. Probability of at most one error, p of x is equal to at most 1, that is p of x is equal to 0 plus p of x is equal to 1, written as 8c 0 p power 0 1 minus p 8 minus 0 plus 8c1 p power 1 1 minus p 8 minus 1. It is 8c0 is 1, p power 0 is 1, 1 minus p whole power 8 plus 8p 1 minus p whole power 7. So correct answer is option 3. Question number 157. So here the given source produces 4 symbols. Source produces 4 symbols with probability 1 by 4, 1 by 8, 1 by 2 and 1 by 2. And the average code length here is 2 bits per symbol. What is the efficiency of the code? So given probabilities are 1 by 4, 1 by 8, 1 by 2 and 1 by 2. Average code length is 2 bits per symbol. Then code efficiency is entropy per code length. Code efficiency is entropy h by average code length L bar. Redundancy is 1 minus code efficiency. These are the formulas for code efficiency and redundancy. So now we need to calculate this L bar. Average code length is given, which is 2 bits per symbol. We need to calculate H, entropy. That is entropy H is equal to sigma pi log to 1 by pi or minus sigma pi log to pi. This is the formula for entropy. Here pi are probability of source symbols. So P1 is 1 by 4, P2 is 1 by 8, P3 is 1 by 2, again P4 is 1 by 2. So on substitution we will get entropy as 15 by 8. Now the code efficiency is H by L bar. So entropy is 15 by 8 by L bar. Average code length is 2. It is 15 by 16. So 15 by 16. None of the options are correct and this question is deleted. Here the code efficiency is 15 by 16, that is 0.93793.75%. This is a code efficiency. Note that code efficiency can never be greater than 1 or 100%. Here they have given 17 by 16. It is not a code efficiency because it is greater than 100%. So this question is deleted because none of the options are correct. Question number 158. In TDMA, the frequency reuse of bandwidth cell is 6 GHz and bandwidth of channel is 2 GHz. So given the bandwidth of channel is 2 GHz and the bandwidth of cell is 6 GHz and they asked the required number of cells is, therefore required number of cells is equal to frequency reuse of bandwidth cell divided by bandwidth of the channel, that is 6 GHz by 2 GHz. Therefore required number of cells is 3. Correct answer is option 2. Next question. The gain of standard horn antenna is 14 dB at frequency of 10 GHz. This horn is connected to a receiver circuit and is used to measure the power from a source operating at 10 GHz. Antenna with unknown gain is substituted for the horn antenna. So one more antenna is connected with the horn antenna. An attenuation of 12.5 dB must be added in the receiver circuit for the indicated output to be same as horn. In the question they have given an attenuation of 12.5 dB must be added in the circuit for the indicated output to be same as that of horn. Then what is the gain of antenna? Given horn antenna gain is 14 dB, extra attenuation of 12.5 dB is added in the receiver circuit for the indicated output to be same when using the horn antenna. This is the given data. Now the gain of antenna is gain of horn plus 12.5 dB, that is 14 dB plus 12.5 dB, it is 26.5 dB. So correct answer is option 3. Question number 160. The radiation pattern of antenna array depends upon. So let us see, in antenna array there are several controls that can be used to shape the overall pattern of antenna array. The first one is geometrical configuration of overall array, whether that array is linear array, circular array, triangular array. So geometrical configuration decides the pattern of antenna array. Next is respective displacements between the elements. Suppose take a linear configuration. What is the distance between two elements? This distance between the elements in an array also decides the radiation pattern. Excitation phase of individual elements and the amplitude of excitation, phase of excitation to the antenna. Radiation pattern of individual elements. What is the radiation pattern of each antenna? Decides the overall radiation pattern. The total number of antennas in the array. Array elements position and orientation in space. So these are the factors that decide the overall pattern of antenna array. One is geometrical configuration, relative displacements or distance between the elements, excitation phase of individual elements, excitation amplitude of individual elements, the radiation pattern of individual elements, the total number of elements in an array, and array elements position and orientation in space. The radiation pattern of array depends on pattern, spacing of the antennas, magnitudes, phases of the signals feeding to the antenna. Therefore, correct answer is option 1. So this radiation pattern of array depends on the pattern and spacing of antennas, on the magnitude and phase relations of signals feeding the antenna. Correct answer is option 1. Question number 161. In an antenna measurement setup, the bench should be kept at a height of dash to avoid spurious signals from the reference plane. When measuring the performance of antenna in a lab or test environment, especially in anechoic chamber or open area test sites, it is essential to minimize the reflections from nearby surfaces. It is essential to minimize the reflections from nearby surfaces such as ground plane or reference plane or benches to avoid multipath propagation of spurious signals. If the bench or support structure is not positioned correctly, reflected signals from reference plane can cause interference with the direct signals, leading to measurement inaccuracies, distortion in radiation pattern, inaccurate gain readings. To minimize the interference, the setup must ensure that reflected rays travel significantly different path length than the directed ray. Now, the minimum bench height to avoid spurious signals is Rd by 2 lambda, where R is the distance from antenna under test to the reference plane or ground or bench. D is the distance between transmitting and receiving antennas. Lambda is the wavelength of signal being used for the test. Correct answer is option 3. Rd by 2 lambda. Next question. It is related to multimode step index fiber having a core radius of 40 micrometer and clad radius of 50 micrometer. The refractive index of core is 1.4 and delta index difference is 10%. What is the light gathering capability of the fiber? So this light gathering capability is nothing but numerical aperture. For a given multimode step index fiber, refractive index N1 is 1.4, index difference delta is 0.1. For multimode index fiber, delta index is N1 minus N2 by N1. So the formula for index difference delta is equal to n1 minus n2 by n1, where delta is 0.1, which is given, n1 is 1.4 minus n2 by 1.4. Now the value of cladding refractive index n2 is 1.26. We know that numerical aperture or figure of merit of a fiber is used to describe the light gathering or light collecting capability of an optical fiber. Light gathering capability or light collecting ability of an optical fiber is nothing but a numerical aperture of the fiber or figure of merit of fiber, where numerical aperture is equal to sine theta a or n1 square minus n2 square. It is approximately equal to n1 to delta, where theta a is acceptance angle. So numerical aperture is equal to square root of n1 square minus n2 square. So n1 is 1.4 square minus n2 square, 1.26 square. Its value is 0.62. 0.62. Correct answer is option 1. Next question. Light guided within the core of step index fiber. How light is guided? Because of total internal reflection at the core cladding interference. Total internal reflection at the core cladding interference. An optical fiber works on the principle of TIR, total internal reflection. For total internal reflection to take place within the fiber, the following conditions has to be satisfied. One is refractive index of core should be greater than refractive index of cladding, and the angle of incidence at the core clad interference should be greater than critical angle. Theta I at core cladding interference, core clad interference should be greater than critical angle. Therefore, light is guided within the core of optical fiber. Total internal reflection at the core cladding interference. Correct answer is option 2. Next question. When a target is moving with a speed equal to the blind speed, then Doppler shift equals to. If the target is moving with a blind speed, then Doppler shift is equal to pulse repetition frequency. So let us see here. The blind speed is defined as radial velocity of target at which MTI radar response is 0. It is defined as the radial velocity of target at which moving target indicator radar response is 0. Blind speed is defined as radial velocity of target which results in a phase difference of exactly 2 pi radians between successive pulses. This is the second definition. Third definition is blind speed is defined as radial velocity of target at which no shift appears, making the target appearing stationary, and echoes from the target are cancelled. Therefore, these are the three definitions of blind speed. The formula for blind speed is Vb is equal to Fp into n lambda by 2, that is n lambda by 2 Tp, where Fp is pulse repetition frequency, n is an integer, it starts from 0, 1, 2, 3 onwards, lambda is a wavelength, Tp is equal to 1 by Fe, pulse repetition interval. Correct answer is option 3. The radar blind speed is the speed at which target will not be visible to the radar. So blind speed is equal to Fp into lambda by 1, lambda by 2 for n is equal to 1. Doppler shift Fd is equal to 2 Vr by lambda. Vr is the relative velocity of radar target along with the line of sight. So Ft, Doppler shift is equal to 2 Vr by lambda. That is equal to Vb, blind speed. Therefore, Fd is equal to Fp. When target is moving at a speed equal to the lowest blind speed, then Doppler shift is equal to pulse repetition frequency. Correct answer is option 3. Next question, question number 165. A lossless transmission line with characteristic impedance of 75 ohms. So given Z0 is 75 ohms and load impedance is 130 ohms. Now the reflection coefficient. Reflection coefficient gamma is equal to ZL minus Z0 by ZL plus Z0. So that is ZL is 130 minus 75 divided by 130 plus 75. It is 55 by 205. 0.268 is a reflection coefficient. Given the magnitude of incident wave V in is equal to 15 volts as ZL naught is equal to Z naught. In the question, this load impedance, characteristic impedance and load impedance are not equal. Therefore, standing waves are formed in the transmission line. The maximum value of voltage in the transmission line is V maximum is equal to V in into 1 plus gamma. This is V maximum. V minimum. Maximum voltage V maximum is equal to V in 15 into 1 plus 0.268. So maximum voltage is 19 volts and V minimum is 15 into 1 minus 0.268. So its value is 10.97, approximately 11 volts. Therefore, the magnitude of maximum and minimum values of voltage on the transmission line is 19 volts and 11 volts. Correct answer is option 3. Next question, question number 166. A dash cavity resonator is most commonly used in dash mode, permits a widest tuning range. A cylindrical cavity resonator is commonly used in TE111 mode in cavity resonators that permits a widest tuning range. Correct answer is option 3. Cylindrical cavity resonator is most commonly used in TE111 mode that permits a widest tuning range. Question number 167. So it is related to Smith chart applications. This Smith chart can be used for lossy lines and the locus of impedance or admittance is spiral. Reflection coefficient and voltage standing wave ratio will vary. Here VSWR and reflection coefficient will vary. The locus of impedances or admittance is spiral. Smith chart can be used for lossy lines. Correct answer is option 1. Question number 168. For a shorted section of 75 ohms transmission line, length is lambda by 4, input impedance is dash. Input impedance of lambda by 2 transmission line is same as load impedance, that is impedance repeats for every lambda by 2 distance. In a lossless quarter wave length line is also known as impedance transformer because it transforms high impedance to low impedance and low impedance to high impedance. Therefore, lambda by 4 line is also used for impedance matching. If the magnitude of input impedance is same as characteristic impedance for the lambda by 8 line, these are the 3 different points for lambda by 2 transmission line, lambda by 4 transmission line, lambda by 8 transmission line. For lambda by 8 transmission line, the magnitude of input impedance is same as magnitude of characteristic impedance. Zn is equal to Z0. In the question they have given lambda by 4 transmission line. For lambda by 4 transmission line, if output is open circuited, then input impedance is 0. If output is short circuited, then input impedance is open circuited, infinity. Impedance inversion takes place. It transforms high impedance to low impedance and vice versa. Here for a short circuited transmission line, so here the load is short circuited, input impedance is open circuited, so that is infinity. Short circuited means open circuited means short circuited at the input. Question number 169. Skin depth and surface resistance for copper at 10 gigahertz are given dash. So we know that skin depth is a measure of depth at which amplitude of electromagnetic wave reduces to 36.8% of the initial value. Skin depth delta is given as, for a good conductor, delta is equal to 1 by alpha or 1 by beta, because in good conductor alpha is equal to beta is equal to omega mu sigma by 2 under root, that is square root of pi f mu sigma. Therefore delta is equal to 1 by square root of pi f mu sigma. Now substitute the values of frequency. So pi frequency is 10 gigahertz, 10 power 9. Mu is mu naught mu r. Take it as mu r is equal to 1 and mu naught is 4 pi into 10 power minus 7, and conductivity of copper is not given. Sigma c is not given. Conductivity of copper is 5.96 10 power 7. So since conductivity is not mentioned in the question, hence the data is given in the question is not sufficient. Therefore this question is deleted from the question paper. We know that conductivity of copper is 5.96 into 10 power 7. On substitution, the value of delta is 6.6 into 10 power minus 4 millimeter. Next is surface resistance or skin resistance. Surface resistance or skin resistance, Rs is equal to 1 by sigma delta. Sigma of copper is 5.96 10 power 7 and delta skin depth is 6.5 or 6.6 into 10 power minus 4 millimeter, 10 power minus 3. So on substitution its value is 0.0257 ohm per meter square, that is 0.026 ohm per meter square. Surface resistance, we know that we have skin depth delta is equal to 6.6 into 10 power minus 4 and surface resistance Rs is equal to 0.26 ohm per square meter. This question is deleted from the question paper. Correct answer is option 1 because conductivity of copper is not mentioned. Question number 170. If an electromagnetic wave is incident on a surface of second medium having different properties, then wave will be. If electromagnetic wave is incident on a surface of a second medium having different properties, then wave will be partially reflected and partially transmitted. If electromagnetic wave is incident on a surface of a perfect conductor, that is second medium is perfect conductor, then wave will be perfectly reflected and no transmitted components. Here it is not a perfect conductor, then it is partially reflected and partially transmitted. Question number 171. Maximal equations of electromagnetics are valid under all conditions except. This Maxwell equations of electromagnetics are valid under all conditions, that is isotropic and anisotropic mediums. It is valid for isotropic and anisotropic medium, linear and non-linear medium, homogeneous and non-homogeneous medium, but these Maxwell equations are not valid for a medium whose characteristics change with respect to system coordinates. So these are not applicable to a media whose characteristics change with respect to the system coordinates. These Maxwell equations are applicable for isotropic media, applicable to non-homogeneous medium, applicable to non-linear medium. So correct answer is option 4, where the characteristics of a medium changes with respect to the system coordinates, there Maxwell equations are not applicable. Question number 172. Maxwell equations that implies magnetic lines that are continuous and that there cannot be any isolated poles on which magnetic lines of force can terminate is. So isolated magnetic pole is for del dot B is equal to 0. Isolated magnetic pole does not exist. Therefore magnetic flux lines are continuous. So del dot D is equal to rho v means Gauss law for electrostatic fields. Isolated electric charge exists. And electric flux lines are discontinuous. Isolated electric charge exists and electric flux lines are discontinuous, where del dot B is a Gauss law for magnetic field. Isolated magnetic pole does not exist, and magnetic flux lines are continuous. Next is del cross H is equal to J bar plus dou D bar by dou T. This is Ampere circuital law for time varying fields. Del cross E is minus dou B bar by dou T, Faraday's law. So here correct answer is there cannot be any isolated pole. That means isolated magnetic pole does not exist and the magnetic lines are continuous. Therefore del dot B is equal to 0. Question number 173. Ohm's law in field theory is Ohm's law in circuit theory is V is equal to IR, whereas Ohm's law in field theory is J is equal to sigma E. This network theory is applicable for a circuit with signal frequency less than 1 megahertz. If signal frequency is more than 1 megahertz, then field theory is applicable for a circuit. In case of field theory, Ohm's law is J is equal to sigma E. For field theory, Ohm's law is equal to J is equal to sigma E. For circuit theory, V is equal to IR is the Ohm's law, and this network theory or circuit theory is applicable for frequency less than 1 megahertz. Question number 174. Dash is a layer that does not have permanent existence. During night time, D layer disappear. F1 and F2 layer combine to form a F layer. Therefore, D layer does not have permanent existence. Correct answer is option 3. So let us see different layers of ionosphere. For D layer, critical frequency is 100 kHz, average height is 70 kilometers and the range is 50 to 90 kilometers. Electron density is 400 electrons per centimeter cube. E layer, critical frequency is 3 to 5 megahertz, average height is 110 and the range is 90 to 140. Electron density is 5 into 10 power 5 electrons per centimeter cube. For F1 layer 5 to 7 megahertz, F2 layer 5 to 12 megahertz. During night time, F1 F2 layers combine to form F layer and this D layer gets vanished. The average height of F1 layer is 220 kilometers and for F2 layer it is 300 kilometers. Electron density in F2 layer is 3.3 into 10 power 5 to 2 into 10 power 6 electrons per centimeter cube. Okay. Correct answer is option 3. Next question. A 75 minus 2J ohm load is connected to a coaxial line of 75 ohm. Impedance at 75 ohm impedance at 5 megahertz. The perfect matching can be obtained by employing. So matching is perfect if load impedance is equal to characteristic impedance, that is reflection coefficient gamma is 0. So if gamma is 0, reflection coefficient is 0, then maximum power transfer takes place. Given characteristic impedance is 75, load impedance is 75 minus 2J. 75 minus 2J. Here minus 2J is capacitive reactance of minus 2J ohm in load. For load to make equal to characteristic impedance, we need to add a small inductive load of plus 2J ohm. We need to add plus 2J ohm so that ZL becomes 75 ohms, which is same as Z0. Now ZL is equal to Z0, matching takes place, maximum power transfer exists. Therefore, we need to add a small inductance at the load. The inductance value is plus 2J ohm. Correct answer is option 3. Question number 176. The depth of penetration of electromagnetic wave in a medium having conductivity sigma at frequency of 2 megahertz is 15 centimeters. The depth of penetration at a frequency of 8 megahertz will be. The depth of penetration or skin depth is a measure of depth at which amplitude of electromagnetic wave reduces to 36.8% of initial value. Skin depth delta is equal to 1 by alpha or 1 by beta. For good conductor, alpha is equal to beta is equal to omega mu sigma by 2 under root, that is square root of pi of mu sigma. Therefore delta is equal to 1 by square root of pi f mu sigma, and from this delta is inversely proportional to square root of frequency. So delta 1 by delta 2 is equal to square root of f2 by f1. Given delta 1 is 15 centimeters and f1 is 2 megahertz, we need to calculate delta 2 for frequency f2 is 8 megahertz. Therefore delta 1 by delta 2, 15 centimeters, delta 2 we need to calculate under root f2 by f1, 8 mega by 2 mega, that is 4, square root of 4 is 2. Now delta 2 is 15 centimeters by 2, that is 7.5 centimeters. Correct answer is option 1. Question number 177. The condition for distortionless transmission line is Lg is equal to Rc. This is a condition for distortionless transmission line. A distortion line is one in which attenuation constant alpha is independent of frequency and phase constant beta is linearly dependent on frequency. Attenuation constant is independent of frequency and phase constant beta is linearly dependent on frequency. The condition for distortionless transmission line is R by L is equal to G by C. That is Lg is equal to Rc. For distortionless transmission line, alpha is equal to under root Rg, beta is equal to omega root Lc. A lossless line is also a distortionless line, but distortionless line is not necessarily a lossless transmission line. Correct answer option 1. Question number 178. This question is deleted. The characteristic impedance of S parameter is. So we know that S parameters doesn't have fixed characteristic impedance. S parameters are defined with respect to reference impedance, which is not intrinsic to the S parameters. The reference impedance is a chosen parameter for a measurement system, typically 50 ohm, but it can vary depending on the system. Examples are, so 50 ohm is for common RF or microwave systems, 75 ohm common broadcast or television, 100 ohms in differential high speed digital systems. So characteristic impedance of S parameters is not fixed. It all depends on the type of system. So this question is deleted. Question number 179. So Brewster angle theta b, it is defined as. So Brewster angle is also known as polarization angle. That is, if any arbitrary polarized wave is launched with a Brewster angle, then perpendicular linear polarized wave gets reflected and parallel perpendicular linearly polarized wave gets reflected and parallel polarized wave gets transmitted. That is, arbitrary polarized wave can be decomposed into linearly polarized waves. So Brewster angle tan theta b is equal to under root epsilon 2 by epsilon 1, that is n2 by n1, because refractive index is equal to square root of permittivity, that is n2 by n1, refractive index in medium 2 by refractive index in medium 1, formula for the Brewster angle. Let us see some more points. For parallel transmission or vertical polarization, Brewster angle is defined irrespective of the medium. So Brewster angle is defined only for the parallel polarization. Irrespective of medium, Brewster angle or total transmission angle can be defined only for the parallel polarization. No Brewster angle for the vertical or horizontal polarization. No Brewster angle is defined for perpendicular or horizontal polarization. Correct answer is option 1. Next question. To improve the conductivity or to minimize the losses inside the waveguide due to roughness or inner surface of the waveguide is coated with. So it is coated with metals with high conductivity. So here gallium arsenide is a semiconductor, zinc aluminum is a metal. Compared to aluminum, gold and silver is having more conductivity. The correct answer is option 4. The inner surface walls of waveguide are coated with high conducting materials, very high conducting materials, that is gold and silver. to improve the conductivity and to minimize the losses inside the waveguide. Correct answer is option 4.